In this video, we are going to look at some numerical integration techniques. So the basic problem is to find the values of integrals of this type, that is integral a to b f of x dx, which are otherwise called definite integrals. Now let's take a very simple case. Suppose we are just finding integral a to b, say cos x dx. Then what is the answer to this? All of us know the answer. It is integral cos x is sin x, and that within the limits b to a will give us sin b minus sin a. So this is a problem where our given function has an antiderivative. So we are able to reach or arrive at the exact solution. That is, this given problem has an analytic solution. But this may not always be the case. For example, suppose if you are dealing with say integral e raised to minus x square, then the problem is integral e raised to minus x square does not have a proper antiderivative. That is, e raised to minus x square does not have an antiderivative as such, analytical. That is, an analytical solution does not exist. So in that case, we will have to find an approximate solution to this given problem. So it is in such a case that such numerical approximations have significance. Another scenario can be, suppose your f of x is not given as an, suppose if it is not given as, f of x is not explicitly given to you as a formula. Maybe it is empirically given to you as a table of values. That is, you have some x values and you have the corresponding f of x values. So maybe x is 0.1, 0.2, etc. and you have f of x values, maybe 2, 5, something, etc. And you are asked to integrate f of x from 0 to 1. Then what will you do? Of course, you cannot use the usual integration techniques that you have learnt until now. You will have to use numerical integration. So this is another scenario where you will have to use numerical integration techniques. Now I'll repeat once more. So where do we usually use numerical integration techniques? One scenario can be where you do not have an analytic solution. Another scenario may be where you are given the function not as a formula but as empirically as a table of values. Now we'll move to the first numerical integration technique, that is the trapezoidal rule. Now here the scenario is we are given with a function f of x and we are asked to integrate that function from a to b. Okay, so suppose I am just having some sort of function like this. Okay, now I have to integrate this function from this point a to this point b. Then what we are going to do here is we are actually going to divide this into subintervals like this. We are going to divide this whole that is limit of integration. We have to integrate it between a to b. So first of all, what is the output? The output is area under the curve from a to b, right? So our main aim is to find area under this curve from a to b. Now we are going to subdivide this whole region into smaller regions like this. So the first point is a or x0. Second point I'm going to call it as x1. Third point I'm going to call it as x2, etc. The last point xn, the last point will be xn or b. Now we are interested in finding the area under the curve between a and x1, between this a and x1. So what we will do is, instead of this curve, we are actually going to approximate this curve using a straight line joining a and x1. Of course, there is an error when we are actually doing that approximation. Now instead of this area under this curve, we are actually going to approximate it as the as a trapezoid that you can see here, that is this given trapezoid. So instead of area under the curve, we are actually going to find the area of this trapezoid. Similarly, when we move on to the next part, we will be approximating the curve by the line joining those two things. Again, similar in the next region, and in all those regions, we are actually going to approximate this curve as the line joining f of a and f of x1. Next will be f of x1 and f of x2, the line joining f of x1 and f of x2, etc. The last point will be f of xn minus 1 and b, that is this given line. And the sum of all these areas will give us an approximate value of the area under the curve. Now let's look at the curve that I have drawn here. Now this is what we are going to do here. We are going to subdivide it into this interval of integration into different points, that is a, x1, x2, etc., xn minus 1 and b. Now we are actually going to approximate this area under the curve from a to b as different sections, that is area under the curve from a to x1 plus area under the curve from x1 to x2, etc., area under the curve from xn minus 1 to b. Now here this approximation is done using the straight line. As you can see here, in this case the error will be very small. Now what is the area of a trapezoid? Suppose you have some sort of a trapezoid like this, and suppose this side is a and this side is b, and suppose the height here is h. Then area under the area of this trapezoid is 1 by 2 a plus b into h, half a into b, half a plus b into h. Okay, so the area of under this curve from a to x1 is going to be 1 by 2 f of a plus f of x1 into h. That is, this given height is your f of a, this given height is your f of x1, and h is this given length of that interval a to x1. So that serves as your height, and the parallel sides are f of a and f of x1. So f 1 by 2 f of a plus f of x1 into h will give you area of this given trapezoid here. Similarly, the area of the next trapezoid, this given trapezoid, that trapezoid is given by 1 by 2 f of x1 plus f of x2 into h. Similarly, the area of the next trapezoid, the x2 or the last trapezoid, xn minus 1 to b, is going to be 1 by 2 times f of xn minus 1 plus f of b into h. Okay. Now, what will be the area under the curve from a to b? Area under the curve from a to b will be the sum of all these trapezoids. So you have to add all these together. Now when we add, here I have 1 by 2 times f of x1, and here again I have 1 by 2 times f of x1. So this will come out to be just f of x1 when you take area under the curve. Next, here there is f of x2. In the next term there will be again half 1 by 2 times f of x2. So that will come out to be f of x2. Similarly, up to f of xn minus 1, the terms will be just 1 times f of x1, 1 times f of x2, etc., 1 times f of xn minus 1. The first term is 1 by 2 f of x. That will come out directly as f of 1 by 2 f of a itself. And the last term is 1 by 2 times f of b. That also will come out as 1 by 2 times f of b itself. All the other terms, since you are having two terms with the coefficient 1 by 2, they will add up and become 1 times f of x1. Okay. Now, hence the area under the curve, the formula is going to be this one, this given formula. Integral a to b f of x dx is h. There is an h term in every of these expressions. So you will keep that h term common outside. 1 by 2 f of a, that is given here, 1 by 2 f of a. Next term is plus f of x1. That is because here you are having 1 by 2 f of x1 plus 1 by 2 f of x1. That becomes f of x1. Here you will be having 1 by 2 f of x2, and in the next term also you will be having 1 by 2 f of x2. So the next term will be just f of x2. In the last term you are having 1 by 2 f of xn minus 1, and the preceding term also you will be having 1 by 2 f of xn minus 1. So the second last term will be f of xn minus 1, and the last term is 1 by 2 f of b. This formula is called the trapezoidal rule. So this you have to know by heart from now onwards. So the trapezoidal rule to find the area under the curve, or to find the integral a to b f of x dx is h into 1 by 2 f of a plus f of x1 plus f of x2 plus etc. f of xn minus 1 plus 1 by 2 f of b. Now I'll go back to that question once more. So that is, first of all, you must understand what are x1, x2 and all these things. We are actually subdividing the given interval into n subintervals. That is very important. We are subdividing the interval of integration into n subintervals like this: a, x1, x2, etc., xn minus 1, b. So h, that is the distance between a and x1, will be b minus a by n. The distance between x1 and x2 will also be h, etc. So we are dividing the whole interval of integration into n subintervals. Thus n will either be given to you in the question, or sometimes you will have to choose it you will have to just take a choice of n, and then divide it into subintervals x1, x2, etc., xn minus 1, and then you will have to find all those values. That is f of a, you will have to find f of a, you will have to find f of x1, you will have to find f of xn, x2, you will have to find f of x3, etc., you will have to find f of xn minus 1, and you will have to find f of b. Now once you have found all those things, you will have to use this formula here to find the integral. It will be clear when we are doing a problem. Now we will discuss one more technique before we move on to problems. The second rule is called Simpson's rule. Here what we are going to do is, in the Simpson's rule, to actually evaluate the area under the curve, say something like this, from a to b. Here also we have to divide this whole interval into subintervals like this. Okay, we are going to divide this whole interval of integration into subintervals. In the previous question, from a to b, instead of this curve, we actually approximated it as a line joining them. Now we will, instead of a line, we will be using a quadratic polynomial approximation. So for that we will be actually using the Lagrange interpolation method, and we will be actually approximating it as a polynomial. So in all these intervals we will be actually approximating the curve as a polynomial. Okay, and then we will be trying to find the area under the curve. Now that involves a derivation, so I am not going to move into those derivations, but I'll just give you the formula here. Now here what we are going to do is, as you can see, we are dividing the interval of integration into subintervals. That is the we have to find integral a to b f of x dx. We are going to subdivide it into 2m subintervals. Usually we are taking n subintervals. So here it should be an even number. That is very important when it comes to Simpson's rule. We have to divide it into an even number of subintervals. Okay, that is a very important thing here. We have to subdivide it into 2m. That is, we can divide it as 4 subintervals, or 6 subintervals, or 8 subintervals, or 10 subintervals. So there will be 2m subintervals. So in trapezoidal rule we are using n subintervals. Here that n should be an even number, so we are instead using 2m as our subinterval. Okay, and f0, fj will be f of xj. That is, the first point is x0 is a. Okay, first point x0 is a. So f0 will be f of x0, that is f of a. The second point is x1. So f1 will be f of x1. Okay, the third point is x2. So f2 will be f of x2. Similarly, it will go on like that. So in the end, fn will be nothing but f of x. And the final formula to evaluate that evaluate the Simpson's rule will be integral a to b f of x dx is h by 3 into f0. f0 is f of x0 plus 4 times f1 plus 2 times f2 plus 4 times f3 plus etc. 2 times f2m minus 2 plus 4 times f2m minus 1 plus f2m. This is the formula. Here it should be clear. f1 is f of x1, f2 is f of x2, f3 is f of x3, etc. It will be clear when we are doing a problem. Now here what we have to do is to just remember this formula. The ordering is like this: 1, then it comes 4, then it goes to 2, then it is 4, then it is 2, 4, 2, etc. It will go on, and the last term will be 2, then 4, then 1. That is the ordering. So what is the ordering of the coefficients? So it is 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, and in the end it will end with 2, 4, 1. Okay, so that is the ordering of the coefficients, and you will have to multiply this whole thing by h3, and the terms are f0, f1, f2, f3, etc., and just multiply them with this coefficients, that is 1, 4, 2, 4, 2, 4, 2, 4, 2. The last terms will be 2, 4, 1. Okay, that you don't have to even remember this formula like this. When we draw the table, it will be clear. Now we are going to move on to problems. We will do a problem with the same problem we are actually going to do with trapezoidal rule and Simpson's rule. And you must remember, when doing that is trapezoidal rule, when comparing trapezoidal rule and Simpson's rule will have less error when compared to trapezoidal rule. Okay, the error will be less. So here we are going to do this question. The question is integral 0 to 1 e raised to minus x square dx. So evidently e raised to minus x square, you cannot evaluate it directly. Okay, so you will have to use some of the numerical integration techniques. But you just, as a note of caution, when it comes to exams, they will sometimes ask integrals which can actually be evaluated, that is, whose solution can be evaluated analytically. But you must just use this method. What you must know is, here we are only trying to study a method. Okay, so sometimes they may ask you to find integral 1 by 1 plus x square dx or something like that, using numerical integration techniques also. So here the importance is in studying this integration techniques. Okay, now what is the first thing that you have to do is, you look at the value of n they have given us 10. So the limit, that is from 0 to 1, this is the length of the interval. This you have to divide it into n subinterval, that is 10 subintervals. So what is the value of h? H is equal to 1 minus 0 by n. That is 1 by 0 by 10. That is b minus a by n. That is your h. That is 1 minus 0 by 10. So that comes out to be 0.1. So you have to divide this with this interval 0 to 1 as subintervals of length 0.1. So how will be the first point will be 0 plus 0.1, which is 0.1. The next point will be 0.1 plus 0.1, which is 0.2. The next point will be 0.2 plus 0.1, which is 0.3. Okay, so that is how you have to subdivide the interval. First point will be x naught, next point will be x naught plus h, third point will be x naught plus 2h, etc. Okay, so you just have to go on and you will reach at 1. So that has been done here. So you can look at this values. First value is 0, second value is 0 plus 0.1, which is 0.1. Next you are adding 0.1, you will get 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. So you have divided the whole interval of integration, that is 0 to 1, that was the interval of integration, with the given n value, that is n is 10. So 1 minus 0 by 10 is 0.1. So h value should be 0.1, and you have to divide the whole interval of integration into subintervals of length 0.1. Okay, now we have done that. Now what is the next step? Next step is, you have to find f of x values at these endpoints. So what is f of x? F of x is e raised to minus x square. Okay, so what will be f of 0? F of 0 is e raised to minus 0 square, which is 1. Okay, next thing is f of 0.1. What is f of 0.1? F of 0.1 is e raised to minus 0.1 square, that is 0.9900. Similarly, we have to find the next value. What is f of 0.2? F of 0.2 is e raised to minus 0.2 the whole square, so that is 0.9607. Similarly, find all the other values, that is e raised to minus 0.3 the whole square, e raised to minus 0.4 the whole square, e raised to minus 0.5 the whole square, etc., e raised to minus 1 square. All these values you have to find out. So we have found all these values. So this is your first value a, you can call it a or you can call it x naught. This is your second value x1. This is your third value x3, etc. This is your last value xn. Now what was the formula? The formula was h into 1 by 2 times h into 1 by 2 times f of x naught plus f of x1 plus f of x2 plus f of x3 plus etc. You will have to reach up to the last value, that is this is f of xn minus 1 plus 1 by 2 times f of xn, or xn is nothing but your b, x naught is nothing but your a. Now this was the formula. So what you have to do is all this value and this value you have to multiply it with 1 by 2. These two values. All the other values you just have to add them as such. That is what is done. First value, last value. You just, if you want, you add them, first value and last value, and divide it by 2. All the other values you have to use it as such and add it. That is what you have to do. So the final answer comes out to be 0.7462. Okay, now that is done. Now we will move on to doing the same question using Simpson's rule. Now when we are using Simpson's rule with length n equal to, that is with number of subintervals n equal to 10. So here what you have to remember is, whenever you are using Simpson's rule, n should be even. Of course n is even, n is 10. So n is 10 or equivalently 2m, that is 10. We are using a different notation here. We are calling n as 2m, since to ensure that it is an even number, we are using 2m. So 2m is 10. Now we have to use the same procedure. We have to divide this whole interval into subintervals of length 0.1. h is b minus a by n. So we have to do the same procedure here. So we have already done that in the previous question. So I'm just going to use that same table. Okay, we have done the whole procedure here. We have divided the whole length into subintervals, 10 subintervals. Now with n points 0, 0.1, 0.2, 0.3, etc. Now we have already found the values also. What were the values? That is, we have found f of x values also here. Now what is the difference between using trapezoidal rule and Simpson's rule? Trapezoidal rule, the rule was this first term and last term you divide it with 1 by 2. All the other terms you just add it, and that is your value of your integral. So integral 0 to 1 e raised to minus x square, you got it like that. Now here, instead of that, the formula is different. The first term and the last term. So the formula is h by 3 into, the terms will come f of x naught plus 4 times f of x1 plus 2 times f of x2 plus etc. It will go on like that. Okay, so I'll just illustrate it in this table here. Now this h by 3, that term will be there outside, that is 0.1 by 3, and then the next term will be this first term and last term. The coefficient is going to be 1. So here and here, these two, the coefficients are going to be 1. So here it is 1, here it is 1. Next, the coefficient of this term, it will be 4 times 0.9900, then 2 times 0.9607, plus 4 times 0.9139, plus 2 times, that is 0.8521, then plus 4 times 0.7788, plus 2 times 0.6976, plus 4 times 0.6126, plus 2 times 0.5272, plus 4 times 0.4448, and then the last term is 1 times 0.3678. So I hope you have got the order. 1, 1, that is the first and the last term. Then the terms will come out like this: 1, 4, 2, 4, 2, 4, 2, 4, 2, 4. Then the last term is 1. This is the coefficient with which you have to multiply. So that has been done here. Okay, you just look at this expression. It has been done here. This is your point h by 3, and the first term is 1 times 1, and the last term is 1 times 0.3678. Then the rest of the term is 4, 2, 4, 2, 4, 2, 4, 2, 4. Okay, so this is how you have to do. Now if you want, what you can do is, all these terms you just take it together, you add them together, and you can just multiply it by 4. And these terms you add them together, and then you multiply it with 2, and the first and the last term you just add them together as such, and then that sum you multiply it with 0.1 by 3. That is your required answer, and the answer is 0.7468. Of course, for doing all this, you will have to use a calculator. Don't do it by hand. Use a calculator. So it's going to be simple. Even finding e raised to minus x square, we are using a calculator. Now this we have done a problem, the same problem using Simpson's rule and using trapezoidal rule. I hope it is clear. Now remember, in exams they may ask you questions for which you have analytic solutions also. But remember, the question is just whether to check whether you know to use these numerical integration techniques. Okay. Now I hope it will be clear. Now you just do some exercise problems and it will be clear in the end. Thank you.